And so we're very glad to have Kim Nguyen here today from Regensburg, talking about covariant and contravariant homotopy theories and Quillen's theorem. So you can start when you're ready, Kim.
Right. Yeah. So thank you very much for the invitation and giving me the opportunity to talk about this. And I guess it's nice to be virtually in Brno. Right. So I want to talk about these covariant contravariant homotopy theories and how they are related to Quillen's theorem A. And the idea is the following. So suppose we have a locally presentable category C. Right, and we have a functorial cylinder object on this. Then we actually get two distinct model structures out of this datum, which behave in a, say, covariant and contravariant fashion with respect to the cylinder. So, and today I want to explain how we can do this and what are the applications in higher category theory. So what we get is two, in general, not always, distinct model structures on C, let's say behaving in a covariant or contravariant fashion. And the motivation for all of this is pre-sheaves. So more precisely, homotopy theory for pre-sheaves in higher category theory. So in general, talking about pre-sheaves in infinity category theory is something that is rather hard. So instead, one takes the vibrational perspective, which is much easier to handle, at least, for example, in the model of quasi-categories. And the way one studies these pre-sheaves then is by studying certain model structures. And these are called the covariant or contravariant model structures. On simplicial sets. Simplicial sets sliced over a simplicial set. And these are supposed to model pre-sheaves on an infinity category A with values in infinity groupoids. And another example is, so these model structures are due to Joyal. And for the case of pre-sheaves with values in infinity categories, one studies the Cartesian and co-Cartesian model structures. These are due to Lurie on marked simplicial sets. So they are modeling pre-sheaves on A with values in infinity categories. Right, and so the point is that both of these examples are instances of a model structure which are generated out of a suitable cylinder object. And so what we get is new proofs for the existence of these model structures. And also some of the theorems become very easy and elementary, especially in Lewis' theory of co-Cartesian model structures. It can get pretty rough pretty fast. So the plan for the rest of this talk is as follows. First, I want to tell you how these model structures are constructed. From a cylinder. And then once we have these model structures, there's a notion of cofinality, which is very natural in this setting. So you get an abstract notion of cofinality, which recovers the usual notions of cofinality of functors. And then there's a characterization of cofinal functors in terms of slices, so contractibility of slices. And a consequence of this is Quillen's theorem A. And I want to explain how we get a, say, a more refined version of Quillen's theorem A using these homotopy theories. Right, so in case you don't understand me and or cannot read, please let me know. So let's start with these model structures from a cylinder. And so the input is a locally presentable category. Say C, and together with a weak factorization system, say LR. And then we can make the following definition. So defining what is a cylinder object. So a cylinder on an object, say X of C, is an object called I tensor X, together with structure maps which are like endpoint inclusions into a cylinder. And then a projection map from the cylinder back to the object. And we want the endpoint, the inclusion of endpoints to be, say, a monomorphism. So we want this to be in the left class. So in all of the examples that we're going to consider, there are either pre-sheaf toposes or something close to it. And then we take as a weak factorization system the monomorphisms and, well, the right class determined by the monomorphisms. Right, and then just as in topology, we want that the following diagram commutes. So we have our cylinder object and the endpoint inclusions. And the projection map. And this should give the identity. Right, and then one further definition is a functorial cylinder object on a category.
Can I just ask him that?
Yeah.
Second map, you didn't ask any condition of it. The map
No.
from tensor X to X.
No condition. Yeah.
Okay, thanks.
Right. Yeah. So a functorial cylinder on C is an endofunctor together with natural transformations denoted in the same way. Goes from the identity times the identity to this endofunctor, and from this endofunctor to the identity functor on C, such that evaluation at any object defines a cylinder on it. Okay, so this is our starting point. This is the datum that we need to generate a model structure. And so to go further, I want to introduce some notation. So whenever we have a morphism, call it I, then we get commutative squares as follows. So we can take the endpoint inclusion into the cylinder object, and then of course the map I itself. That's the cylinder applied to the morphism, and then also another endpoint inclusion. And we also get, instead of including both sides of the cylinder, we're just including one. And from these commutative squares, we get induced map from the push-out product. So in the first case, that's then a map. Like so. And in the second case, that will be a map. Like so, right. And so there's one final assumption, or 2, 3 final assumptions that we need to make to get this theory going. So finally, we assume that the cylinder satisfies the following properties. So first of all, we want this to commute small colimits. And for each morphism I in the left class of the factorization system that we started with, then the induced maps from the push-out products. And I should have given them names. So I'm going to call this map boundary of the cylinder times I. And this is one inclusion times I. And we want those maps to be in the left class again. Right, and now what we're doing is to generate the smaller structures is we're giving ourselves a class of trivial cofibrations. So this is not all of trivial cofibrations, but this class is large enough to recognize the fibrant objects. So we make the following definition, say, we pick a class of morphisms in the left class, then A is called a class of right I anodyne extensions if the following conditions are satisfied. So first thing is what you want is that A is a saturated class. And this is generated as a saturated class by a small set of morphisms. And then second condition is if we are given a morphism in the left class, then we want one of the pusher products to preserve morphisms in this left class. Oh no, sorry. So if we are given a morphism in the left class and we apply this pusher product to it, then we want it to be a right anodyne extension. And the third condition is if we are starting with a right I anodyne extension, then the other push-out product preserves this. So, so for this definition of right iodine extensions, we are just using one of the inclusion of into the cylinder and not the other one. And right, so that's the idea, to get this covariant or contravariant dependency on this cylinder. If we would have included, say, the other, say, delta 0, so the other endpoint of the cylinder, then we would have called this left anodynes. So let's just write this down. Then we get left I anodyne extensions instead of the right ones. And okay, I realize this seems to be a very definition heavy talk. Another definition is, so first of all, observe, given a small set of morphisms, say S in the left class, then you can generate out of it a class of right or left anodyne extensions just by closing up under the operations of the push-out product and then taking the saturated class generated by it. So it generates a class of right I anodyne extensions. And let's denote this by anodyne right depending on I and S. And so I said that this is going to be the trivial cofibrations, which are large enough to recognize when an object is fibrant. So make the following definition. So a right IS fibration is a map having the right lifting property with respect to this class of right underlying extensions. All right, now finally, then there's the theorem. And so some of you might have recognized that it's, I mean, you may have recognized all of this already. So that's due to Szyczynski, I guess. Well, it is in a more strict form where you require both endpoint inclusions. And then he proved it, I think, for pre-sheaf topoi and topoi. And then Mark Olschok proved this for locally presentable categories. And then I sneaked in and observed that everything goes through if we just forget one of the axioms, and then we get the following. So there exists a monostructure on C such that the cofibrations are given by the class L, the left class of this weak factorization system, and the fibrant objects are the right IS fibrant objects. And then we can say a little bit more because from this theory, we don't really get control of the trivial cofibrations, or this is going to be cofibrant generated, but we don't really get a control of the generating trivial cofibrations. But at least what we can do is we can recognize the fibrations between fibrant objects. So moreover, the fibrations between fibrant objects are precisely the right IS fibrations. Okay, and so let's look at some examples because these examples are, the idea is really that we get all of these examples that I mentioned before out of this theory without putting in a lot of work. So the first example, probably one that everyone is familiar with. So if we take simplicial sets and we take the SA factorization system, the monomorphisms, and those with the right lifting property with respect to monomorphisms, which are usually called trivial fibrations. And we take as a cylinder object just the Cartesian product with delta 1 and the set of morphisms which generate these right anodyne extensions. Just take the empty set. Then what we get is just the Quillen model structure. And so here you see, this is an example where really the direction of the cylinder doesn't really matter. And the reason is because we're thinking of this simplicial sets as simplicial sets over the point. And so in particular, it's over an infinity groupoid. And in an infinity groupoid, the direction of the cylinder gets inverted. Or you can invert the cylinder. So the direction here doesn't matter. But a little more interesting then is if we take simplicial sets over a given simplicial sets, and again, monomorphisms and Fourier fibrations as a factorization system, then the cylinder is induced from taking the Cartesian product. So I'm going to just draw a diagram for this. So what we do is, as a cylinder, is we first take the projection to an object over A, and then composing with a structure map. That's how this cylinder works on the slice category. And again, take the empty set to generate these anodyne extensions. Then we get Girard's contravariant model structure on the slice category. So this is a model structure modeling pre-sheaves on A with values in infinity groupoids. So the fibrations, let me tell you what the fibrations are. And this is where we get the name from. So these are right fibrations with target A. So just to recall, so right fibrations are those maps of simplicial sets where you can lift against Horn inclusions, and here K is supposed to live to be strictly greater than 0, but can be N. So this models pre-sheaves on A with values in infinity groupoids. Right, and then finally, so you can also do the following example. Now you take marked simplicial sets. So let me remind you what marked simplicial set is, unless there's any objections. So the category of marked simplicial sets. So this has objects, pairs, say X, EX. And X is supposed to be a simplicial set. And EX is a set of one simplices. And these are supposed to contain all the degenerate one simplices. And then if you have a simplicial set A, then we get two marked simplicial sets out of it. So the first one is A flat, where only the degenerate simplices are marked. And A sharp, where all one simplices are marked. Okay, and now in this setting, take simplicial sets over a marked simplicial set. Take as a weak factorization system, again, monomorphisms and those with the right lifting property with respect to those. And now as an interval, we take Cartesian product with delta 1, and I mean there's only one non-degenerate 1 simplex, and you mark it. And now for the set generating our anodyne extensions, we want to take inner Horn inclusions. So we are forcing the underlying map of simplicious sets for the fibrant objects to be inner fibrations. So and then we want to make sure that whatever we do, the equivalences will be marked. And this J is the nerve of the free walking isomorphism. So then what we get is the Cartesian model structure on this category, which is due to Lurie, and in fact, he proves this in the case where the target is of the form A sharp, so where every edge is marked, just because that's the only thing that he needed. I'm pretty sure that he could prove many other things. So let me tell you what the fibrant objects here are. So the fibrant objects are maps where the map of underlying simplicious set is an inner fibration. And the set of marked edges is precisely the set of Cartesian arrows lying over the markings downstairs. So in particular, if you take as a target a marked simplicious set where all edges are marked, then the fibrant objects are Cartesian fibrations. Over A, and these are modeling pre-sheaves on A with values in infinity categories. So this is the infinity categorical analog of a Grothendieck fibration, and the right fibrations are the infinity categorical analog of groupoidal Grothendieck fibrations. Okay, and I mean, so the nice thing is that once we have proven this abstractly for a just general cylinder object on a locally presentable categories, we sort of get all of these different examples for free. You can also get a version of the dual model structure where you take as an interval the free walking isomorphism and you force the inner anodyne morphisms to be trivial cofibrations. Then you get something where the fibrant objects are isofibrations, and over the point, this is precisely the dual model structure. And for this free walking isomorphism, what happens is that because it's symmetric, then the left and the right notions again coincide, so it doesn't really matter. But in these examples, it really it's really important that we consider one of the inclusions and not the other one. So for example, right, so in this example, we get pre-sheaves. If we would have taken the covariant model structure where we force the other inclusion to be a trivial cofibration, then the fibrations are the left fibrations. So we are modeling co-pre-sheaves with values in infinity groupoids, and here we get co-pre-sheaves with values in infinity categories. Okay, so questions so far?
Yeah, maybe. Does this construction transfer along adjoints in some sense? So if you know you have all that structure on a category and you have an adjoint pair or maybe even a geometric morphism, say, to another category, can you just transfer everything?
It's a good question. I don't know. I actually have never considered this. I mean, in these cases that here, they do somehow transfer. You have, so, right, so you can go from here, say from simplicial sets over A, you can get to marked simplicial sets over A sharp, and this will be a right Quillen functor. But I actually have never considered it as sort of like more abstractly in terms of adjoint pairs between different categories. It's a good question. Yes, I don't know.
All right, thanks.
Great. So then move on. Let's move on with cofinality. So we can just abstractly define what a cofinal morphism is from these model structures, and it's inspired by what you do in infinity category theory. So definition, let's say a map in this locally presentable category, say from A to B, is called cofinal if for all objects X and all maps from B to X, the induced map in the slice category is a, so I'm going to call it covariant equivalence. So that's when we apply this covariant model structure to the slice category. So it's something that in all slices becomes a weak equivalence. So that's the definition. And there are some examples which you can give right away, just out of the theory. The canonical examples are well, the left iodine extensions. It's just how these model structures are constructed for all these different slices. And also the class R, which plays the role of trivial fibrations. And in fact, these are in some sense all the examples. So a morphism is cofinal if and only if can be factored as, say, if we're taking this example A to B, you can factorize it as a left I anodyne extension and some map in the class R. So in particular, what you get, I mean, just from the definitions that you recover notion of cofinal functor for infinity categories. And then there's the dual notion of a final functor, where you just require it to be a weak equivalence in all these contravariant model structure instead of the covariant ones. So again, you get sort of like for free a dual pair of a final and a cofinal functor. And then along with this, then there's the map of the notion of a smooth and a proper morphism that we can also define in this abstract sense. So let's make one final definition. So let's take a map from X to Y. And suppose we have Cartesian squares. The following form. Give these two morphisms a name. Then this morphism from X to Y is called smooth if for such diagrams, whenever J is cofinal, so is the morphism I. It's just the mimicking definition for, say, for simple sets of categories. And then something a little bit more interesting happens, is that these covariant and contravariant model structures, they sort of interact with each other. And you can show that the right I fibrations always satisfy this condition for a certain class of anodyne extensions. Say for a nice class of left I anodyne extensions. And the nice class is something which looks like a deformation retract. And these deformation retracts are always preserved under pullback along a right fibration. And dually, if you have a left fibration, then it will always be so proper, so that this condition is so the same condition where we require final maps instead of cofinal ones. So left and right fibrations are always close to being proper. And in the examples that I care about, they are actually. So let's look at another example. The example is the following. So, say in this covariant, contravariant model structures, on these slice simplicial categories, so including over the point, then we recover the usual notions of final and cofinal functors, and the say the smooth maps well, not the, I want to say right fibrations. You can show that right fibrations and Cartesian fibrations, that they are smooth and dually left fibrations and co-Cartesian fibrations are proper. So that's, I mean, I think that's something that I've first seen in Lurie's book, where he proved that. And I mean, the proof is rather complicated because it involves the Groton deconstruction to prove it, or at least a small version of the Groton deconstruction. And the upshot of all of this, if there is, if there is any, is that there's a very elementary proof that you can give using this theory of these covariant and contravariant model structures. It's just inside of simplicial sets, some small combinatory argument, and then you're basically done. And here's another example which may or may not be interesting. Is this time let's construct another model structure, and this time what we want to model is pre-sheaves with values in n types. So let's say consider say the contravariant model structure associated to the following data. So we take as a cylinder, again, Cartesian product with data 1, and then we just throw in one morphism that we require to be a trivial cofibration. And that's the boundary inclusion. Then, in this case, the fibrant objects are right fibrations with n-truncated fibers. So a pre-sheaf with values in an n-type. And then we again get a notion of final co-final morphism for free. And then these notions of co-final morphisms you can use to define weaker notions of co-limits and limits. And that's so like, I guess that's the point I want to make. So it can be used to define weaker notions. So for instance, so define, say, an n initial object in an infinity category C, or a simplicial set if you want, to be a n cofinal map from the point to C. So n cofinal is then the notion of a cofinal morphism with respect to this so like localized model structure. So being an n initial object is something weaker. It satisfies a weaker universal property than being actually initial. So instead of having a contractible mapping space out of it, you would just have a connected mapping space. So so the universal property just stops at some point. So for example, a one initial object is just an initial object in the homotopy category or associated to this infinity category. So why would we care about these sort of weaker notions of limits and co-limits? And so the reason for me, at least, is that has to do with adjoint functor theorems in the higher categorical setting. So you can prove the following, and that's due to myself, George Raptis, and Christoph Schrade. So suppose we have a functor between infinity categories and assume C has finite limits and F preserves them. Then F has a left adjoint if and only if we take the slice under an object D of D, and this has supposed to have a 1 initial object for all objects D of D. So that's one version of an adjoint functor theorem in the setting of higher categories. I mean, in one categories that would be trivial, right? So for one categories that would just mean it has a left adjoint if and only if the condition of having a left adjoint is satisfied. But because in infinity categories here you have this more freedom upstairs, you can require stronger and stronger notions of initiality to formulate different versions of adjoint functor theorems. So you get, for example, the classical general adjoint functor theorem, which would involve something like a zero initial object, or not quite a zero initial object, but this weakly initial set where you just require morphisms to exist out of them, which corresponds to zero initiality. And then as a corollary, which I find nice, from this adjoint functor theorem is that if you have a functor as above, then F has a left adjoint if and only if the induced functor on homotopy categories does. So I mean, this is something which might be familiar for equivalences, so that you can check equivalences of infinity categories on the homotopy category level. And right, and here we can improve this a little bit so that we can check adjunctions when we can lift the adjunctions on homotopy categories to the infinity categorical level. Right, so finally, let me finish with Quillen's theorem A. So remember, Quillen's theorem A, which says that if you have a functor between ordinary categories, then it induces, and we want to have a condition when does it induce an equivalence of classifying spaces. So then F induces homotopy equivalence of classifying spaces if when we take slice category, and this is contractible for all objects in D. So that's the classical Quillen A. And in modern language, that's actually a consequence of a characterization of cofinal functors. So this is a consequence of the following. And that's due to Troyal and written up by Lurie. I mean, many things are due to Troyal, but you just never can find it. So a functor between infinity categories now, that's cofinal if and only if the slice category is contractible. So remember, being cofinal just means that it's a weak equivalence in all the slices. So in particular, in the slice over the point, and there we get just the Quillen model structure. And this just means that in this model structure, it becomes a weak equivalence. So it's an equivalence of classifying spaces. And then here's a refined version of this. When you apply this to these truncated model structures. So then a functor is n cofinal if and only if the slice category is n connected. And then from this you get a corollary a functor between one categories induces an n-connected map of classifying spaces if this slice category is n-connected. Okay, so I'm almost out of time. I actually did plan.
That's a question, actually.
Yes.
I'm just confused by the statement of Quillen's theorem. You've got like C over D.
Yes.
This shouldn't be F over D or something. Am I confused?
Oh yeah. It's probably right. You could have that's sort of imprecise notation, I guess. So what I call C over D is probably what you call F over D, and that's the pullback.
Yeah. That's right.
Yeah. Right.
Okay.
So in particular, what you get is if you apply this, say for one categories, you just recover this usual characterization of an ordinary final cofinal functor where the slice category is connected, right? It's non-empty and connected. That's what you get from this more general version of this theorem, and that's like one of the instances where you cannot just apply infinity category theory and drop it on just ordinary category theory and get the right notions back, because in this case it does not, simply because you can. It has to do with limits and co-limits, and they differ in the infinity or one category sense if your target is not a one category. So from this theory, and I was very ambitious, and I actually planned to show you a proof of this because it's so easy, but now I'm out of time. But just to get the point across that all of this is rather easy, and it is, it's not super deep mathematics and it's not super hard mathematics, but I somehow felt that this was nice, that it works out in this very abstract way, and you can combine lots of different theories into a single framework. And sometimes it's just nice to have nice things. And right, so I'm going to finish with this. Thanks for your attention.
Okay, thanks very much for a nice talk. So we usually have a silent round of applause, or rap your knuckles silently on the table, whatever. So if anyone wants to ask a question, go ahead. I could have a comment then. I don't know if it's really relevant, but Simon Henry has these weak model categories where he looks at his definition of interval at the start, sort of prioritizes one of the inclusions to the interval object.
Oh, okay. I was not aware of this.
Yeah, I don't know if it's directly related, but so if you haven't looked at it,
Yeah.
it might be interesting to look at
All
and
right.
see if there's any.
Yeah, thanks. Yeah. I didn't know.
No, it's kind of weird because in his axiomatization of a weak model category, he only requires that he prioritizes one of the inclusions over the other one.
Mm-hmm.
But then later, ultimately, it proves that the other inclusion is also weak equivalence.
I see.
So I don't know if it's fundamentally imbalanced, but in your case, there seems to be some intentional imbalance.
Yes, there is, and one thing that happens that this functorial cylinder, it is not a cylinder object in Quillen in the model category sense, just because the projection is not a trivial fibration. See, so for these right fibrations, say you have the projection from a simplistic set times an interval to the simplistic set itself, right? So the fibers are the interval itself, and if this interval is not contractible, then that's not a trivial fibration. So it does not define a cylinder object in the model category sense, but it can still be used to define homotopy equivalences, and then you get the homotopy theory going from this point of view.
Quillen's definition of cylinder only required that map to be a weak equivalence, right?
Yeah, right.
But so are these weak equivalences? Or
no.
They're not even weak equivalences.
Yeah, they're not. They're not.
Yeah, I also maybe have a question. So this theorem of Joel and Lurie, you state here.
Yes.
Of course, the left part, you gave a general definition, your framework, right? In a locally presentable category with all that structure, you can define what a cofinal functor is, right?
Right.
Right-hand side doesn't really make sense, right?
Right.
But can you generalize the theorem where it does make sense? Say maybe you have an infinity cosmos or something.
Yeah, I'm not sure about this. So I mean, the right-hand side, where this comes from, is that what you do is you have a factorization from the map from a point, and you factorize it into right iodine and right vibration, for example, and then you get these. So the point is that these are, I mean, ultimately what we want to say is that this is a homotopy Cartesian square somehow, and right. And so if we just take a general category, then I guess what you need to do is understand what you put in this place. So what's the right thing to factorize it over? I mean, the proof will probably work in the same way to give a characterization. I just don't know what exactly I should put there. Another example is that for these Cartesian co-Cartesian model structures, I would also like to know what the final cofinal morphisms are there. I just never got around and understood it. And hopefully it would have something to do with, say, lax limits and co-limits. But I just don't know.
Yeah, thanks.
Yeah.
I have a little question too.
Yes.
Could you go back to your statement of the adjoint functor theorem, please?
Yes, I can.
Yeah, maybe you actually already said this and I missed this, but I'm not sure. So what happens if you replace the one initial object with a higher n initial object? What does it look like?
So it gets more complicated, and that's why I didn't state it. So I mean, you can sort of like generalize this in two ways. So either you require a stronger condition here, or you require a weaker condition here. So we are actually preserving infinity categorical limits. And the only way that we thought about this up to this point is that keeping this one and then requiring a weaker, so requiring preservation of weak limits. So in the sense that I've just given you in terms of, say, n final or cofinal morphisms. And then we get also adjoint functor theorems, which can be recognized on homotopy n categories instead of the homotopy category, for example. But we don't have a version where we give a stronger condition here, and because we then didn't know what to do with the other side, really.
Okay.
So I guess the answer to the question is I did not say anything about this.
So
at
ideally,
all.
it should look like something like a stronger preservation of limits. Sort
Yeah.
of like, okay. Thanks.
Any more comments or questions? Well, if not, then let's thank Kim again for that excellent talk.
Thanks again for the opportunity.
No problem. And Regensburg isn't so far, so hopefully you can come visit someday or something in the future. So,
Yeah, hopefully, yes.
Great. And okay, so next week we have Walter Tolan talking at 2 p.m. So it'll be an unusual time. Okay, so we can stop recording then.